There is a wall at the edge of the universe. Not a physical wall. Not a barrier you could touch or see or crash into. But a boundary so absolute, so mathematically certain, that nothing, no light, no signal, no information, can ever cross it to reach us. And here is the part that should stop you cold. We have no idea what lies beyond it. This is not a gap in our technology. It is not a failure of our telescopes. It is a fundamental limit baked into the laws of physics themselves. The universe beyond that boundary is not hidden from us because we haven't looked hard enough. It is hidden from us because the light from that region has never and will never reach us. Not in a billion years. Not in a trillion. Not ever. So the real question is not what the observable universe looks like. We actually know that with stunning precision. The real question is what it means that the observable universe is only a fraction, possibly an infinitely small fraction, of what actually exists. And what scientists have found when they start pulling on that thread is either the most profound discovery in human history or the most unsettling possibility we have ever confronted. Let's go beyond the edge. Most people have a vague sense that the universe is big, incomprehensibly big. We hear numbers like 93 billion light-years and nod as if that registers, as if our brains can actually hold that thought. They cannot. No human brain can. The distance from Earth to the Moon is roughly 1.3 light-seconds. The distance to the nearest star is over 4 light-years. The Milky Way spans roughly 100,000 light-years end to end. The nearest large galaxy, Andromeda, sits 2.5 million light-years away. And the observable universe stretches 46.5 billion light-years in every direction from where you are sitting right now. But here is where the story changes. We did not always know the universe was this large. For most of human history, we thought the Milky Way was everything. The entire cosmos, one galaxy, one island of stars, and nothing else. Then in 1924, Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory in California to resolve individual stars inside faint, fuzzy patches of light that astronomers had been cataloging for decades without truly understanding. He showed that these smudges were not clouds of gas inside the Milky Way. They were entire galaxies, each containing hundreds of billions of stars, sitting millions of light-years beyond our own galaxy's borders. The universe, in a single observation, became hundreds of thousands of times larger than anyone had imagined. But Hubble wasn't done. A few years later, he made a second discovery. The galaxies weren't just sitting there. They were moving. And almost all of them were moving away from us. The farther a galaxy was, the faster it was receding. This wasn't the motion of objects flying through space. This was the fabric of space itself stretching, expanding, carrying everything inside it along for the ride. This discovery, that the universe is expanding, is what creates the boundary we started with. Think about what expansion means. If space itself is stretching between us and distant galaxies, then at some distance, the rate at which that space stretches actually exceeds the speed of light. This is not a violation of physics. Einstein's relativity says that nothing can move through space faster than light. It says nothing about the space itself expanding faster than light. And so, at a certain distance, roughly 46.5 billion light-years in every direction, galaxies are being carried away from us so fast that even light they emit today will never, ever reach us. That is the observable universe. Not the universe. The observable universe. The slice of it from which light can still travel to us. Beyond that boundary, space is expanding too fast. Light from that region is running toward us and losing ground forever. It is the cosmic equivalent of trying to swim upstream in a current that gets stronger the farther out you go until one day, no matter how fast you swim, the river is simply too fast. And the universe beyond that wall keeps going. How far? We don't know. The honest, scientifically rigorous answer is, we genuinely do not know. Our models allow for a universe that extends far beyond our cosmic horizon. They allow for a universe that is hundreds of times larger than what we can see. They allow for a universe that is infinitely large. All three options are consistent with what we observe, and we cannot currently distinguish between them. But here is what makes cosmologists lie awake at night. Some of the most well-tested theories in physics don't just allow for a universe larger than what we can see. They essentially demand it. The theory is called inflation. In the first fraction of a second after the Big Bang, and when we say fraction, we mean a time so small it makes a billionth of a second look like an eternity, the universe underwent a period of exponential expansion so extreme that it makes today's expansion look like a gentle stretch. In something like 10 to the negative 32 seconds, the universe grew from a size smaller than a single proton to something roughly the size of a grapefruit. That doesn't sound impressive until you do the math and realize that if a proton expanded at the same rate, it would end up larger than the observable universe. Inflation was not proposed because cosmologists wanted a wild idea. It was proposed to solve three very specific, very real problems with the standard Big Bang model. The first problem was smoothness. Look at the cosmic microwave background, the faint afterglow of radiation left over from when the universe was 380,000 years old, and you find that it has almost exactly the same temperature in every direction. 1 part in 100,000. The problem is that regions on opposite sides of the sky have never been in contact with each other. They are separated by distances so vast that not even light could have traveled between them in the entire history of the universe. So how are they the same temperature? How did they reach the same equilibrium if they've never interacted? Inflation solves this by saying they were once in contact, they were once part of the same tiny region, and then expansion tore them apart and carried them to opposite ends of our sky. The second problem was flatness. The geometry of space can be curved. It can be positively curved like the surface of a sphere, where parallel lines eventually converge. It can be negatively curved like a saddle, where parallel lines diverge. Or it can be flat, perfectly Euclideanly flat, where parallel lines stay parallel forever. Our measurements of the universe show it is extraordinarily flat, with a deviation of less than 0.5% from perfect flatness. This is a problem because flatness is an unstable condition, like balancing a pencil on its tip. The slightest deviation in the early universe would have grown catastrophically over time, resulting in a universe that either collapsed in a big crunch or expanded so fast that matter never condensed into galaxies. For the universe to be this flat today, it had to be tuned to extraordinary precision at the beginning. Inflation provides a natural explanation. A balloon inflated to cosmic scales would appear flat from the inside, just as the curved surface of the Earth appears flat to someone standing on it. The third problem was the absence of magnetic monopoles. Standard physics predicted that the Big Bang should have produced vast numbers of exotic particles called magnetic monopoles, particles that have only a single magnetic pole, north or south, but not both. We have never detected one. Inflation solves this by diluting them to such low density that encountering one in the observable universe would be essentially impossible. 3 problems. 1 solution. Inflation solves all of them elegantly. This is why most cosmologists take it seriously despite the fact that it describes events we can never directly observe. But here is where inflation becomes genuinely disquieting. If inflation happened, it almost certainly didn't happen uniformly everywhere. The quantum fluctuations that caused inflation to end in our region may not have caused it to end elsewhere. In some regions, inflation may have continued, may still be continuing, and regions where inflation continues expand so fast that they are forever beyond any horizon, forever disconnected from everything that exists in our observable universe. These regions can spawn their own pockets of space where inflation eventually ends, their own universes with their own properties, their own physical constants, their own laws. This is called eternal inflation, and it leads directly to the idea of a multiverse. Not a multiverse in the science fiction sense. Not parallel universes where another version of you made different choices. Something stranger and more fundamental than that. Universes where the speed of light is different. Where the mass of the electron is different. Where atoms cannot form because the electromagnetic force is slightly too weak or too strong. Where stars cannot exist because gravity tuned itself to a different value. Universes that are vast, empty, cold, and dark. Universes that flash into existence and collapse before a single particle of matter can coalesce. An endless, unimaginable foam of space-time regions, each one a cosmos unto itself, forever isolated from every other, forever unknowable. This is what lies beyond the observable universe if inflation is correct. And we cannot prove it. This is the tension at the heart of modern cosmology. Inflation is the best explanation we have for the structure of the universe we observe. But the universe it implies, a universe of universes, a multiverse vast beyond calculation, is by definition untestable with current physics. We cannot see beyond our cosmic horizon. We cannot receive a signal from another inflationary bubble. We cannot confirm or deny the existence of other regions of space where inflation ended at different times with different values for the fundamental constants of nature. Some physicists argue that this makes eternal inflation and the multiverse not science at all, that a theory which makes no testable predictions is closer to philosophy or theology than physics. Others argue that the evidence for inflation is so. The largest known structure in the observable universe is called the Hercules Corona Borealis Great Wall. It is a filament of galaxies spanning approximately 10 billion light-years, roughly a tenth of the diameter of the observable universe. Its existence challenges our models of how structure forms, because standard cosmology suggests that structures this large shouldn't be able to form in the time the universe has existed. Its true extent may be even larger, and it sits at such a distance that studying it in detail is extraordinarily difficult. And yet, this is all still inside our cosmic horizon. This is all still the observable universe. Beyond it, the same structures presumably continue. Filaments, voids, superclusters, the slow and ancient clockwork of gravity sculpting matter across scales that beggar description. For how far? In principle, the universe we cannot see could contain structures vastly larger than anything we have detected. Voids wider than the observable universe itself. Filaments that dwarf the Hercules Corona Borealis Great Wall the way a highway dwarfs a thread. If the universe is infinite, and current observations are consistent with an infinite universe, then not only do these structures continue forever, but every configuration of matter that is physically possible occurs. Somewhere, infinitely far beyond our cosmic horizon, there is a region of space where matter has arranged itself into something that looks exactly like the Milky Way galaxy. And inside it, a solar system that looks exactly like ours. And on the third planet, a version of you reading exactly this sentence. Not a copy. Not a parallel version in some quantum branching sense. Simply another arrangement of particles that happens, by the sheer brutal arithmetic of infinite space, to be identical. This is not mysticism. This is combinatorics. If space is infinite and matter is distributed according to rules that allow only a finite number of configurations within a given volume, then every configuration must repeat. Not once. Infinitely many times. The physicist Max Tegmark calculated the distance to the nearest identical copy of you in an infinite universe. The answer, based on the number of possible quantum states in a volume the size of the observable universe, is roughly 10 to the power of 10 to the power of 28 meters. A number so large it is meaningless to write out, but finite. And in an infinite universe, that distance is crossed, again and again, forever. Let that breathe for a moment. Now, here is the layer of the mystery that science is only beginning to probe. The expansion of the universe is not slowing down. It is accelerating. Something, and we call it dark energy only because we have no better name and no true understanding of what it is pushing space apart at an increasing rate. Not just expanding, accelerating in its expansion. The farther away a galaxy is, the faster it recedes. The faster it recedes, the sooner it crosses our cosmic horizon and vanishes from our observable universe forever. And as time passes, more and more galaxies will cross that horizon, carried away by dark energy, disappearing beyond the boundary from which no signal can ever return. The observable universe is shrinking. Not in size, in content. Galaxies that are currently visible will eventually cross the horizon and vanish, not because they move through space, but because the space between us expands too fast for their light to bridge. In the distant future, tens of billions of years from now, the night sky from a planet in the local group will be nearly empty of other galaxies. Astronomers in that era, if they exist, will look out at a universe that appears almost entirely uniform and nearly empty. Without the records we might leave behind, they would have no way to know that billions of galaxies once filled their sky. They would build models of a universe that is static, bounded, and alone. They would be wrong, and they would have no way to know it. This is, perhaps, the most haunting implication of our cosmic horizon. We exist at a uniquely privileged moment in cosmic time. Privileged not in a spiritual sense, but in an observational one. The universe is young enough that the evidence of the Big Bang is still visible. The cosmic microwave background still reaches us. The distribution of galaxies still encodes the physics of the early universe. The grand structures of the cosmic web are still mappable. Future observers, in a cold and expanded cosmos, will inherit a universe stripped of this evidence. The story will be gone. Only local matter will remain, isolated in a dark and featureless void, with no way to reconstruct what came before. We are, right now, in the best era that will ever exist to understand the universe. And we still don't understand it. We don't know what dark energy is. We don't know what dark matter is. Dark matter, the invisible substance that makes up roughly 27% of the universe's total energy content, holds galaxies together, sculpts the cosmic web, and leaves its fingerprints in the motion of stars and the bending of light. We cannot see it. We cannot directly detect it. We know it exists because of what it does, the way you know there is a wind by watching the leaves move, never seeing the air itself. We don't know if the universe is infinite or finite. We don't know if inflation happened. We don't know if there are other regions of space beyond our horizon. We don't know what, if anything, preceded the Big Bang. We don't know whether the fundamental constants of nature are truly constant, or whether they vary across regions of space we cannot observe. These are not minor gaps. These are not details waiting to be filled in by the next generation of telescopes. These are foundational questions about the nature of reality, and we have been staring at them for decades without resolving them. This should fill you with something. Not despair. Not frustration. Something richer than both of those. Because here is the thing about standing at the edge of human knowledge and looking out at what we cannot see. It means the universe is larger than us. Not just physically. Larger than our concepts. Larger than our models. Larger than the mathematics we've invented and the instruments we've built and the theories we've tested. The universe refuses to be contained by any framework we bring to it. Every time we extend our reach, we find more horizon. Every time we answer a question, we find 10 deeper ones waiting beneath it. The observable universe, 93 billion light-years across, containing 2 trillion galaxies, each holding hundreds of billions of stars, each star potentially hosting worlds, this entire, staggering, incomprehensible volume of space and time and matter may be, in the grand scheme of what exists, essentially nothing. A bubble. A local clearing in a fog that extends forever. A single note in a symphony that has been playing for longer than time itself, in scales we will never fully hear. We are a civilization that has existed for roughly 10,000 years on a small rocky world orbiting an ordinary star in the outer arm of one galaxy among 2 trillion. We are young and clever and curious and small. We have pointed our instruments at the sky and measured the echo of creation. We have mapped the shape of space. We have detected the ripples that black holes leave in the fabric of reality when they collide a billion light-years away. We have done extraordinary things. And the universe has responded, quietly, with the same answer it always gives. There is more. There is always more. Beyond the wall of the observable universe, space continues. Structure continues. Matter continues. Perhaps other universes bud off from the fabric of space-time and expand into their own eternal silences. Perhaps the physics we know applies everywhere. Perhaps somewhere out there, across distances no number can represent, the constants tuned themselves differently and a completely alien kind of complexity arose. Something that thinks, something that looks outward at its own cosmic horizon and wonders what lies beyond it, something that asks the same question we are asking right now, and receives the same silence in return. We will never know. That is not a failure. That is the shape of the universe. The boundary exists not because the universe is hiding from us. It exists because the universe is old enough and large enough and expanding fast enough that its edges have outrun their own light. We are not excluded. We are simply finite. Finite creatures, with finite instruments, inside an infinite space, trying to read a story that began before time and may never end. What we can do is keep looking, keep measuring, keep building the telescopes and the detectors and the theories. Keep pushing the models until they break and then figuring out why they broke and building better ones. Keep mapping the 46.5 billion light-years we can see with the same rigor and wonder we would bring to an infinite universe, because in doing so, we learn the language that the rest of existence speaks. The observable universe is not our cage. It is our window. And on the other side of that window, in every direction, in every moment, something vast and ancient and indifferent and magnificent continues to unfold. We just can't see it yet. And maybe that's exactly how it should be.